Alrighty, hello everyone. In this video, we will take a look at how to determine the empirical formula of a given compound. And if you recall, we've talked previously about the empirical formula and how it gives us the simplest ratios of atoms in a given compound. So let's consider an example. If we have something that has a molecular formula, the molecular formula gives you the number of atoms that are actually present in that molecule. So suppose you have a compound that has the molecular formula C2H6O4. So now that shows us the exact number of atoms present in that particular molecule. If we're looking at its empirical formula, it would give us the simplest ratio. So think of it, can we divide, everything by a whole number? So it looks like we could simplify it by dividing everything by 2. So we'd get carbon H3O2. So then that's what we refer to as the empirical formula. Now, you could have multiple molecules that have the same empirical formula, right? Think of a molecule that has the molecular formula C4H12O8. It would have the same empirical formula, right? So the empirical formula is simply giving us the simplest ratio of atoms present. Are the molecular formula and the empirical formula different? Always different? No. If we consider something like methane, which has a molecular formula CH4, well, if we're trying to figure out its empirical formula, we can't really divide by any whole number. So the empirical formula is the same as its molecular formula. So now how do we determine the empirical formula of a molecule? What do we need? We need the mass of the elements that are present in that particular molecule, or the mass percent composition, right? And we're going to take a look at 2 examples. All right, so we can determine it from the masses of the elements that are present, all right? What we do initially is we take the mass of that particular molecule or element that we're looking at, and we need to convert the mass into moles. What is it that we learned about that has a correlation between mass and moles? Correct, it's the molecular weight or the molecular mass, which has units of grams per mole, right? So anytime you need to convert between moles into mass or mass into moles, just keep in mind the molecular weight is very useful, right? And the molecular weight of the molecule is simply, or the molar mass, just as a refresher, the molar mass of an element is really has to do with the mass of the individual atoms. So let's just consider water, right? If you wanted to determine the molar mass of water, we have 2 atoms of hydrogen, so 2 times. If you take a look at the periodic table, hydrogen is in group 1A, and it has an atomic number of 1, and the atomic mass of hydrogen is 1.01, I believe, right? And that has units of grams per mole. And then we also have oxygen, right? But we only have 1 of oxygen, so we're adding the mass of oxygen, which is 15.99, again, grams per mole. So if we add both up, we'll get the molar mass of water, which if we round it up, really, it's 18 grams per mole, right? So the molar mass, you're not always told you need to calculate it, but just keep in mind that that's something that you may need to think, oh, I need the molar mass, and then calculate the molar mass based on the given atom or molecule that you're dealing with, all right? But if we're dealing with only the element, then it's simply the atomic mass of that element, right? Okay, then what do? We're gonna calculate the number of moles because empirical formula is giving us the simplest ratio. We want the simplest one to be equal to 1. So we'll see that we divide by the smallest number of mole calculated. And then because we can't have like half an atom, we're going to, or, you know, it has to be a whole number. We're going to multiply everything by an integer. So let's actually take a look at how we do something like that. So we're going to consider an example of water. So we already know what we're looking at, but we're just going to take that as an example. So it's water. And suppose you're told that a sample is decomposed to give 0.857 grams of hydrogen gas and 6.86 grams of oxygen gas. And you're asked to determine the chemical formula, right? Well, the chemical formula gives us the mole to mole ratio of the elements. Now, we're already told what the chemical formula is, right? But again, it's just the purpose of calculations. So what we start off with is the actual mass, right? So we're told that we have 0.857 grams of hydrogen gas. Well, if we need to determine the chemical formula or the empirical formula, we need to figure it out in terms of the number of moles of each element that are present. So anytime we have grams, we would need to convert grams into moles, right? So by that, we take a look at where hydrogen is in the periodic table. It's in group 1A in period 1, has an atomic number of 1, right? But then if you take a look at its atomic weight or its molecular weight, it's 1.01. So for every mole of hydrogen, we have 1.01 grams of hydrogen. And remember that molecular weight is simply a ratio. We could say that we have 1 mole of X, I'm just going to call it compound X, per you know, well, actually, let's just use hydrogen. I could say that I have 1 mole of hydrogen per 1.0 grams of hydrogen, or I could say that I have 1.01 grams of hydrogen over 1 mole of hydrogen, right? Think of it much like when you thought of conversion factors, like in an intro to a chem class, where it's simply a ratio, right? When do we use 1 mole over grams versus grams over mole? It depends on what you're given and what you're looking for in a given problem that we're trying to solve, right? So we're multiplying, and then what happens is then our grams cancels out grams, right? And we're left with moles of hydrogen. And we do the same for oxygen. We have 0.8757 grams of oxygen. And if we take a look at it, it's 1 mole per 16 grams of oxygen. And hydrogen and oxygen are both diatomic molecules, right? Okay, 0.429 moles of oxygen. So now what we do is we divide both by the simplest number of moles, or the smallest number of moles. We have 0.429 moles of oxygen, and we have 0.849 moles of hydrogen. Right? So it's basically telling us that for every 0.849 moles of hydrogen, we have 0.429 moles of oxygen. Well, if we want it into a whole number, we are going to divide both moles by the smallest number. And in this case, 0.429 is the smallest of the two. Okay. So we would divide both by 0.429. And then you would get 1.98, and oxygen is 1, right? So in this case, you know, it's close enough to 2, and 1 is 1. So that gives us the chemical formula, which is also the empirical formula of water. Okay, so now suppose we have a more complex example and we're looking at fructose that has the chemical formula C6H12O6, right? The empirical formula of it is the simplest ratio. So it looks like we could divide everything by 6. We'd get CH2O. Its molecular formula is CH2O multiplied by a number, which we're going to call N. How can we calculate N, right? Well, N is equal to the molar mass of the molecule. So if you're given the molar mass, you could find out the empirical formula, and then from there, you can calculate the actual molecular formula, right? And N is equal to the molar mass of the actual molecule divided by the molar mass of the empirical formula, right? How do we calculate those values? Well, the molar mass of the empirical formula is similar to how we did water a little bit ago. We take the mass of carbon on the periodic table, which is about 12 grams per mole. We take the mass of hydrogen, I'm just rounding up for now. We take the mass of oxygen, right? But we have 2 hydrogens, so we're really multiplying this value by 2, and then we're adding everything up. That would give us the molar mass of this empirical formula, right? And if we know the molar, if we're actually given the molecular weight of the actual compound that we're interested in, then we use that, divide that by the empirical formula, and we get what N is equal to. So let's consider the example. All right. So if we calculated the empirical formula and we calculated its mass, molecular weight, we'd get 30.03 grams per mole. And if we're given that in the actual molecular weight, then we could calculate what N is, right? And in this case, it's 6. So we can multiply the empirical formula that we get by 6, and that would give us the actual molecular formula of the molecule. So now let's consider we're actually starting from percent by mass, and we would like to determine the empirical formula of the molecule. Okay, well, it says the elemental mass percent composition of ibuprofen is 75.69% carbon, 80.8% hydrogen, 15.51% oxygen, and it wants you to determine the empirical formula of ibuprofen. Now, the empirical formula is the simplest ratio of each atom, right? And we said that we could determine that from taking grams into moles. And then from there, we're going to divide by the smallest number of moles to get the mole to mole ratio, right? So if you have percent by mass, what does it 75.69% carbon means? It means that we have 75.69 grams of carbon per 100 grams of ibuprofen, right? 75.69% carbon in ibuprofen is the same as saying that we have 75.69 grams of carbon per 100 grams of ibuprofen. And it's a percent, so we're really multiplying by 100. All right. So then it's also equivalent to having 75.6 grams of carbon, right? Because grams is canceling out grams, or 100 is canceling out 100. So what we have really is 75.69 grams of carbon, right? And what we have then is also 8.80 grams of hydrogen and 15.51 grams of oxygen, right? Well, now let's consider 1. and we'll just take a look at carbon. If we need to convert the mass of carbon into grams of carbon, what do we need? How can we convert from grams of carbon into moles of carbon? Yeah, we would need to use the molecular weight, right? We're going to need to multiply it by the molecular weight to get the moles of carbon, right? So would we do 1 mole over grams of carbon or grams of carbon over moles of carbon? Right, we're going to put moles of carbon per grams of carbon. Again, that is the atomic weight of carbon, all right, from the periodic table. It's not a molecule, it's just the atom, so it's the atomic weight of carbon. And it's 12.0 grams of carbon, right? So then grams cancels out grams and we end up with the moles of carbon, right? So let's actually take a look at how we do it, right? So we're given the mass percent composition. So we're going to convert the element masses into moles, and we're going to do that by looking into its molecular weight, right? And then that would give us the moles of each atom, right? Well, because we want to determine the empirical formula and we need the simplest ratio of each of the atoms, and we can't have half an atom of oxygen, for instance, what we do is we find which of those values is the smallest, and then we divide everything by the smallest value, and then one of those would end up equaling to 1, right? So, and that would be the moles of oxygen, because the moles of oxygen is basically the smallest, right? So if we divide everything by the moles of oxygen, which is the smallest number of moles, which in this case is the moles of oxygen, we end up getting the following ratios, all right? So we have 6.50 moles of carbon per 9 moles of hydrogen per 1 mole of oxygen. Okay, well, we cannot have something that is less than, like, something that's not a whole number. And we don't want to round 6.5 into 7, right? Don't want to round. So we need to multiply everything by a whole number that will end up giving us a whole number for everything. So what would we multiply with? By 2, all right? We're going to multiply by an integer. In this case, we're going to multiply by 2, right? So we multiply everything by 2. So we get, for carbons, we have 13 carbon atoms, we have 18 hydrogen atoms, we have 2 oxygen atoms, and that would be the empirical formula of ibuprofen. Right? That's the simplest ratio of atoms of ibuprofen. Right? I hope this was helpful. I will see you next time.